I'm Sam Gunn, and I'm going to be talking about my work with Andrea Colodangelo on an object that we call quantum state indistinguishability obfuscation. This is a joint talk, so the second half of this video is going to be James Bartosek talking about his work on actually constructing this object with Vinod Vaikunthanathan and Zvika Rakerski. So the motivation for this talk comes from the question, what could we do with a fully functional quantum computer? So we have a lot of ideas for this, like quantum simulation for chemistry, Shor's algorithm for factoring large integers, and quadratic speedups all over the place. But all of these applications have to compete with their classical counterparts. So for instance, DeepMind's AlphaFold does a reasonably good job at protein folding. So if you want your quantum computer to be useful for quantum simulation of protein folding, then you're going to at least have to outcompete AlphaFold. So, okay. In this talk, we're going to think about a totally different approach to using a quantum computer, and that's to use the unclonability of quantum states. So the oldest example of this is quantum money due to Wiesner, and that's where you try to build a quantum state that you can sort of test, but that you can't copy. There's copy protection due to Aronson, and that's where you can encode a function or a program in a quantum state that lets you evaluate the program without giving you the ability to copy the program. And then there's one-time programs which allow you to encode a circuit into a quantum state that lets you run the circuit once before it self-destructs. Okay, and crucially, none of these things are even possible with classical information. You can't prove any of these things secure in a classical computational model because you can always copy classical information. Okay, and I also want to mention that it's in principle possible that you could build any of these primitives without achieving quantum computational supremacy. Okay. Naturally, there's been a lot of interest in this area of unclonable cryptography, but it's been notoriously difficult to get provably secure constructions of any of these unclonable primitives listed on this slide. So in this talk, we're going to try to improve on the state-of-the-art understanding of unclonable cryptography, and in particular copy reduction, and while also improving the state-of-the-art constructions of secure copy reduction schemes. The focus of this talk is going to be on copy protection in particular. So copy protection was initially introduced by Aronson, and a copy protection scheme, CP, is a scheme that takes a function f and outputs a quantum state that allows you to compute f on arbitrary inputs, but cannot be copied. Okay, so what do we mean by cannot be copied? Before I can give you a good definition of the inability to copy a function, I need to establish some notation. So we're going to, throughout this talk, fix a universal quantum evaluator circuit, eval. So eval is just a circuit that lets you run any other quantum circuit by feeding the description of the other circuit as input into eval. Okay, and a state psi is going to be called a quantum implementation of a function f if eval of psi in x is equal to f of x on all inputs x. Okay, so in other words, this means that psi is a description of the function f, whether it's a classical description or quantum description. With eval specified, I can give you a definition of copy protection. So we say that a copy protection scheme is secure if no efficient adversary can win the following security game. And winning the following security game corresponds to like copying the function. Okay, so let psi be CP of f, the copy protected state. We're going to give the state to the adversary, and then, as is common in unclonable security games, we're going to split the adversary into two parts, and then we're going to give each part a random input x. Okay, and we say that the adversary wins if both parts of the adversary output the correct output f of x. Okay, and security says that they can't do this, so that the probability they both output the right value is negligible. Okay, but there's many subtleties with this definition. So first of all, should you have to guess all of x, or should you just be asked to guess like one bit of x or something? Also, what is the distribution over x? So for some types of functions, the uniform distribution might not be very interesting and you'd want some other distribution. Okay, and another issue is that maybe the most interesting applications of copy protection are for copy protecting functions that don't really have any cryptographic nature. So for instance, if you wanted to copy protect a video game, you wouldn't really be able to hope to prove that your game was like that your scheme was like cryptographically copy protected. Okay, but we're going to see that quantum state indistinguishability obfuscation, or QSIO, will give us an alternative perspective on copy protection that avoids all of these subtleties. So let's define QSIO. Suppose that rho and rho prime are quantum states that describe the same function, that implement the same function. So recall that means that eval of rho on x and eval of rho prime on x are equal for all x. Okay, so QSIO of rho is going to be, and QSIO of rho prime are going to be new implementations of the same functionality. So QSIO of rho describes the same function that rho and rho prime do, but QSIO of rho and QSIO of rho prime are indistinguishable. So they're indistinguishable implementations of the same function. So what that means is that if I obfuscate rho and I obfuscate rho prime, then you give both these obfuscations to any efficient adversary. The adversary can't tell which order that they received the obfuscations in. Okay. So that's okay. So how does QSIO relate to copy protection? Well, it turns out that QSIO is actually best possible copy protection. Okay, so what I mean by that is that if it's possible to copy protect a function at all, then QSIO of f is copy protected. So it's kind of a strange statement. It doesn't say whether or not QSIO of f is copy protected, but it says that it's at least the best you can possibly do towards copy protecting f. It's at least as good as any other scheme for copy protecting f. Okay, so why? Well, suppose that CP is a secure copy protection scheme for f. Well, if an adversary can copy QSIO of f, then they can copy QSIO of CP of f by the security of QSIO. That's because f and CP of f are functionally equivalent. So if the adversary can copy one, then they can copy the other. Okay. So it follows that QSIO of f is at least as hard to copy as CP of f. Okay. Okay, so we've seen that QSIO is best possible copy protection, but that still leaves the question of whether or not it actually is copy protection for any concrete classes of programs. So we shouldn't be able to hope to prove that QSIO is secure copy protection for arbitrary programs, because some programs might be learnable, some programs are learnable. So if you can learn a description of the program just from the input-output behavior, then you certainly can't copy protect it. Okay, but for some restricted classes of programs, maybe we can prove that QSIO is copy protection. For instance, we already know that there exist copy protectable pseudorandom functions under plausible assumptions. A natural question is whether we can prove directly that QSIO is copy protection for such PRFs. And the answer is yes. In fact, we can go further. So by constructing this proof of that QSIO is secure copy protection for PRFs, we actually find that it gives us ideas that allow us to extend the class of copy protectable programs using QSIO. It turns out that the class of programs for which we can prove that QSIO is copy protection is called puncturable programs. So the idea of puncturing was introduced by Sahai and Waters in a paper called How to Use Indistinguishability Obfuscation, which was the inspiration for the title of our paper. Program F is called puncturable if for every input x we can find a description of an efficient algorithm, f sub x, that lets you compute f everywhere except for x. Okay, and it needs the cryptographic property that the description of f punctured at x, or f sub x, does not reveal any information about f of x. So it's like, can you give out a description of the program that lets you run it everywhere except for one spot? Okay. If a program is puncturable, then in our paper, we show that QSAO is a secure copy protection scheme for F, assuming the existence of one-way functions. And also, depending on the exact kind of puncturing, this may require the additional assumption that unclonable encryption exists. Basically, depending on what, if you allow some sort of information to be revealed about F, then you might need then you need this unclonable encryption. Okay. Now that we've seen all these exciting applications of QSAO, it's natural to wonder whether we're just getting these because we're asking for some totally unrealistic object that doesn't really exist. So to address this, in our paper, we give a construction of the black box version of QSAO that relies on black box obfuscation for quantum circuits. So the thing that distinguishes black box obfuscation for quantum circuits from black box QSAO is that it doesn't necessarily work for quantum descriptions of quantum states. But we show that nonetheless it's sufficient to give black box QSAO. Okay, but still, black box obfuscation for quantum circuits is a very strong assumption, and in particular, we don't even know how to heuristically instantiate any such encryption scheme, such obfuscation scheme. So, but fortunately, in subsequent work that you're about to see, they give a construction of QSAO that just relies on black box obfuscation for classical circuits, which in particular we do know how to heuristically instantiate. So now the second part of this video will be about that.
Okay, so now I'll discuss our work, quantum state obfuscation from classical oracles. And this is joint with Zvika Brakersky and Vinod Vaikuntanathan. So getting right into the main result, well, we define a quantum program Q to consist of both a circuit as well as some auxiliary state psi. And we run this program on some classical input X to produce some classical output Y. And an obfuscated version of such a program consists of both an obfuscated circuit as well as an obfuscated auxiliary state. And these obfuscations should hide as much as possible about the circuit and the state, but the program should still execute correctly. So if we run it on input X, we should get the same output Y. Okay. So our main result can be summarized as the following. Assuming quantum secure one-way functions, there exists ideal obfuscation for any pseudo-deterministic quantum program in the classical oracle model. So there's a lot of terminology to unpack here. So first of all, a pseudo-deterministic quantum program is one in which each input X produces a deterministic or a nearly deterministic output Y. Okay, so it essentially computes a classical truth table or something very close to some classical truth table. Ideal obfuscation refers to the notion of security which we achieve, which says that the obfuscated program should be able to be simulated just given black box access to this functionality described by Q. Okay, so this is essentially saying that the obfuscated program hides everything except for the functionality of Q. Okay, and this in particular implies the notion of quantum state indistinguishability obfuscation described by Sam in the previous talk. Okay. Now, as you might be aware, there are some impossibilities in the literature for achieving, such a strong form of obfuscation, this ideal or virtual black box obfuscation. And the reason we're able to actually prove our scheme satisfies this is because we are also operating in an idealized model, which is this classical oracle model. So the classical oracle model is something that has a long history of study now in quantum cryptography. And it's basically a model in which obfuscation for classical functionalities, classical circuits, comes for free. And so our obfuscator in this model is allowed to include an oracle, which can be prepared by the obfuscator, which computes some efficient classical functionality F. And so the adversary is only allowed black box access to this oracle. Now, this oracle essentially functions as an idealized version of a classical obfuscation of F. And we know that idealized obfuscation doesn't exist in the real world. But if we want to, arrive at an obfuscation scheme in the real world, what we can do is we can replace the oracle with a post-quantum indistinguishability obfuscation of F. And there are several candidates for this that exist in the literature. And it's a plausible heuristic to assume that the resulting quantum state indistinguishable obfuscator is indeed a secure obfuscator. We just don't know how to prove this rigorously yet. The only thing we know how to prove is that this scheme is secure in this idealized model. Okay. Good. So finally, just to put this context in, or put this result in context, the most relevant prior work is from last year due to myself, Kitagawa, Nishimaki, and Yamakawa, where we constructed obfuscation for classically described pseudo-deterministic quantum programs, also in the classical oracle model, but assuming learning with errors. So our improvement over this work is twofold. First, we can generalize classically described to quantumly described programs, so those that include this auxiliary quantum state. And this is important because this is what allows us to achieve all of these applications that was described by Sam previously. And then we also weaken the assumptions. So instead of having to assume learning with errors in the classical oracle model, we can get away with just assuming one-way functions. Okay. So let's move on to just like the high level picture of what our obfuscation scheme looks like. So referring to this program as Q, our obfuscation of Q consists of some encryption of the description of Q, which makes sense because Q is exactly what we're trying to hide, along with some oracle that depends on the decryption key for this encryption scheme. Okay. And the basic idea is that to evaluate this obfuscated program on an input X, the first step will be to somehow take this encryption of Q and produce an encryption of the output Q of X. So perform this computation Q, using the oracle to help us perform this computation. And then finally, since we want the output in the clear, we will again use the oracle to help us decrypt this final ciphertext to obtain Q of X. Okay. Now, if we think about this from an adversarial perspective, there's already a couple interesting observations we can make. So first of all, this computation that produces the output Q of X must be completely blind. That is, the adversary shouldn't be able to learn anything about Q or anything, about the intermediate states of this computation while performing this computation. Okay. So this motivates the need for something called blind quantum computation. And then another really important point is that, notice that we're using the oracle to help us decrypt this final ciphertext. Okay. But it's important that we can't just use the oracle as a secret key for decrypting anything, right? Because otherwise the adversary would be able to decrypt, say, this, initial ciphertext, which would leak the description of Q. So in other words, the oracle should allow us to decrypt some ciphertexts, but not be allowed to decrypt other ciphertexts. So this should function as some sort of constrained secret key. And now to achieve this, we're going to use something called verifiable quantum computation, wherein the evaluator will actually prove to the oracle that they've computed their output ciphertext honestly before the oracle will agree to help them decrypt the output. Okay. Good. So in order to obtain this notion of verifiability, instead of an encryption scheme, we're actually going to use an authentication scheme. So we're going to actually authenticate the description of this program and include that authenticated version in the obfuscation. And now authentication allows us to say that, if I have the key of the authentication scheme, I can actually detect whether the authenticated information has been changed or tampered with, right? Remarkably, actually, quantum authentication, so an authentication scheme for quantum data is known to actually automatically also be an encryption scheme for quantum data. Okay, so we're not losing any privacy by using an authentication scheme. And now the basic idea is that by using the key to this authentication scheme, the oracle will be able to detect at each step of the computation whether the adversary has deviated from the honest computation. Okay, so this is how we achieve this notion of verifiability. Now, due to lack of time, I will point you to the paper for a description of how we actually instantiate this template. But there's really two main questions that are yet to be answered, which is how do we authenticate quantum information? So we design an authentication scheme using essentially random CSS codes or random subspaces that satisfies this notion of publicly verifiable authentication. Okay, and so again, I'll point you to the paper for details about how we do this. But then the second question that we have to answer is, once we authenticate the data, how do we actually perform computation over the authenticated information? So how do we perform computation on this data that is encoded into random CSS codes? And again, this will be answered in the paper, but essentially we build on techniques that were introduced in the context of fault-tolerant quantum computation to show how this can be done. Okay, so let me wrap up by just mentioning really two main questions for future work. And one is something I've already alluded to, right? We're only able to prove the security of our scheme in the classical Oracle model. So if we model the classical obfuscator in this idealized way, but we can hope to prove this scheme or maybe a closely related scheme, assuming only some concrete assumption on the classical obfuscator, for example, that it's a post-quantum indistinguishability obfuscator. So this remains open and a really important direction for future work. And then the other direction will be to say, can we continue to broaden the class of circuits that we know how to obfuscate? So can we generalize beyond pseudo-deterministic quantum programs, for example, to sampling circuits? So quantum circuits that output arbitrary distributions over classical outputs. And so this is something that we still don't know how to obfuscate. And then furthermore, can we even obfuscate programs that take quantum inputs and produce quantum outputs? Here, there's some partial progress from a few years ago showing how to obfuscate programs with very few number of non-Clifford gates. But as of now, we're still fairly far away from saying, the most general statement we can hope to make, which is like, if I'm handed some arbitrary quantum operation, quantum map, can I give you an obfuscated version of that map? Okay, so thanks a lot for listening.